So my talk will be about quantum position verification. And before I start with quantum, let me first talk about position verification. So what is position verification? Imagine you have the following scenario. You have a certain device, and this device wants to, say it wants to access some service that should only be available in a certain location, for example, somewhere in a shopping mall or something like this. And there are several devices placed strategically around the shopping mall. And this device now communicates with all these devices in such a way that these devices should be convinced afterwards that well, let's call them with names. So these are the verifiers and this is the prover. So the verifiers should be convinced that the prover is indeed in the middle or in whichever location it claimed to be. And the idea of how we realize this is to base this on the speed of light. So we want to make sure that it is not possible to answer the questions sent by the verifiers in time unless you are exactly in that location. This is a bit similar to distance bounding, if you know distance bounding, except that distance bounding is a simpler case because the prover will be close to one verifier and tries to show that he's close, so he just has to answer right away. So the first question we can ask about position verification is it possible at all? And my presenter broke. Let's try another one. So, and for answering this question, let me draw some generic protocol in a one-dimensional world. So we have two verifiers. In the one-dimensional case, 2 is enough, and a prover in the middle, and he wants to convince them that he's in the middle. So in this protocol, in general, the verifiers will send two values, x and y, to the prover, and so this axis is time. At the moment when they reach the prover will perform some pre-agreed computation on them and send the answers back to the verifiers, and at this point in space and time, the verifiers should get the answer, and they check, is it indeed the answer they wanted? So any protocol can be cast in this form, at least any one-round protocol. But whatever I say generalizes to multi-round protocols as well. Let's see how we can attack this protocol. So in an attack, we would have that there is no prover in the place where he's claiming to be, because otherwise he would be allowed to succeed. But we are in the setting where the prover is not here, but there's an adversary who has one device here and one device here. But since he doesn't have a device here, he should not be able to succeed in answering the questions from the verifiers in time. So what does he have to do? First, the two adversary devices will get x and y at this point in time. And they have to send back f of xy and g of xy at these points of times. And we have to figure out what they do here. Well, it turns out to be very simple. The one adversary device forwards x to the other, and the other forwards x to the first. And they also keep x and y. And just in time, they have x and y to compute the answers and forward them on. So this breaks the generic protocol. And unfortunately, this easily also generalizes to the 3D case. It generalizes to any number of verifiers, so it's not just restricted to having two verifiers. It works even if we have computational assumptions, like if the prover is polynomial time and so on. There's one exception that if you, there's the exception that you can, if the devices are limited in how much information they can actually transfer or process when it passes by, then there are protocols. All this is due to Chandran, Goyal, Moriarty, Ostrovsky. The problem with this is that these protocols can be broken by one device that has a very high transfer capacity, that's a mirror. So the model is a bit restrictive then. So we can ask, can we get rid of these problems? And indeed, there seems to be a nice way out, namely quantum cryptography. Because if we think again of the attack, this is like the middle of the picture we had here, see, there. We had that this adversary forwards x and keeps x, and this adversary forwards y and keeps y. So it means the adversary copies the values x and y. In the classical case, this is totally okay. But in the quantum case, we have the so-called no-cloning theorem that says, in general, you cannot just clone values. So if x or y, or both of these values sent by the verifiers to the prover, are actually quantum states, so for example, some photons in certain polarizations, if you want to think about something concrete. So little light pulses sent through a polarization filter would be the things we talk about here. So if one of these signals is a quantum state, then the generic attack that I showed you does not work. Of course, that does not mean that there's no other attack. And unfortunately, Burman, Shadran, Fair, Gelles, Goyal, and Ostrovsky, and Schaffner, without T, showed that there is a generic attack against these kinds of protocols, even if we use quantum mechanics. Because what the adversary can do is he can use some very tricky quantum mechanical effects and so-called entangled photons that are, well, if you know what it is, you know it. If you don't, I'm not going to try to explain. But they are tricky things. There are tricky things that go on and that allow you to break this protocol. However, the amount of so-called entangled photons that these two need to share is exponential. So this does not yet rule out that there may be a protocol that is secure against computationally limited adversaries. But at least we have ruled out information theoretically secure protocols too. They also showed a protocol, improved later by Thomas Michael Fair, Kaniewski, and Wehner, where in the quantum crypto setting we can get some guarantees. And since my protocol is an extension of this, I will shortly explain to you how this protocol works. After I have a drink. So their protocol does the following. We have it has the same scheme of two verifiers sending something and the prover having to send answers back. But what we send are different things. So the first verifier sends a quantum state to the prover. So think of it as a bunch of photons, each polarized in a random direction. And the second verifier sends a basis in which to measure these photons. What does it mean to measure photons in a basis? Well, it means if we think about polarization filters, it's not necessarily done that way, but kind of. It tells you for each photon whether you should measure it with a polarization filter that is like this, so you check whether it goes to a vertical filter, or you check whether it goes to a diagonal filter. And now quantum mechanics has this weird property that if you use a certain basis, so a certain collection of filters to measure these photons, you will find out something about these photons, but you will not be able to try it with a different collection of filters. They are gone, and that's the law of quantum mechanics. So what the prover does is he gets this quantum state, he gets the basis, and he measures the directions of the photons according to these filters. And he will get some information, and depending on the filter, it will be different information. And then he's supposed to send the answers back. And the verifiers check, because they produced the photons, they know what the right answer is, they check whether the answer is correct. And this photon at least does not, this protocol does not admit an obvious attack, but there are attacks, but they need these so-called entangled photons. But it can be proven if there are no entangled photons, so this is what they did, or not very many, in this protocol execution, then the protocol is secure. There are two drawbacks. Well, the first is the assumption of no entangled photons, because with today's technology, you can actually create pairs of entangled photons and send them around, and that seems to be enough to break this protocol. I have not talked to an experimentalist how difficult this is in practice, but it seems like a borderline thing to assume as a technological assumption. And the second drawback is that their security proof applies to the 1D case, but no, well, the protocol seems to work in the 3D case too, but no proof is no. So now, finally, I come to our protocol. And it is a small but important modification of the protocol I showed you before. So here's again the protocol from before. We have the quantum state, we have the basis. And the attack against the protocol from the slide before, if you have entanglement, is based very crucially on the fact that this verifier knows the basis. So instead of giving him the basis, we remove the basis from, sorry, let me say again. The attack is based on the fact that the adversary next to this verifier knows the basis. Yeah, I mean, the verifier is allowed to know what he wants. But, so instead of sending this basis, the verifier sends two bit strings x1 and x2. And at the point when they meet, so when the prover receives x1 and x2, he XORs them, hashes them, and this will be the basis that he uses for measuring the state psi. And in fact, this protocol avoids all the known attacks. That's good already, at least if the adversary is polynomially bounded. And we can even prove it secure in the random oracle model. I have no clue how we can prove this secure if H is not a random oracle. That's highly interesting future work, but yeah, I don't know how. But let me try to convince you why this protocol is secure in the random oracle model, at least. So let's look at this protocol. So again, we have the situation that this verifier sends the quantum state, so the photons, and x1, this verifier sends x2. And now you can look for and this is the space-time diagram. So these are how the signals go. Here is how the answers come, and we know there's no prover here. And the prover needs to get these answers right. And the first thing we can observe is that there's no point in space-time in this area where x1 and x2 are simultaneously known. Here x1 is known, here x1 may be known, here nothing may be known, here x2 may be known, but the first point in space-time where x1 and x2 are known in the same location is this point. So we know also that x1 XOR x2 is not known anywhere in any point in space-time up to here. x1 XOR x2 will not be known. So no adversary can guess x1 XOR x2 anywhere here. Here he can, no problem. And this allows us to use programming of the random oracle here. So what we do is, since the adversary does not, so let me first use classical intuition here. Classically, we would think of the random oracle as something that is sampled whenever we access it for the first time at a certain location. And since x1 XOR x2 is not known in this area, it means the adversary can never query h of x1 XOR x2. So until this point, this will still be uninitialized, so we can just program it with a random value b. So at this point in time, we change the value of the random oracle, and the adversary will not be able to notice that. Now, this reasoning is not valid in the quantum setting, because in the quantum setting, the adversary could query the random oracle in one query on a so-called superposition of values, so on all values at the same time. This will give him like all the answers at the same time, and this is pretty useless because they are together in some bunch. But it's not obvious to see that he can't anyway notice that we changed this random oracle when he uses these superposition queries. Fortunately, we can prove that this works. We can do this programming, and everything is fine. So now we have programmed the random oracle here, and nothing has changed. I mean, the attack probability hasn't changed, but the basis in which to measure is now randomly chosen at a later point. That's very important. And now we do a second thing. We put in a light barrier. So we put in some wall here between the two verifiers in the middle, and no information can go through this wall. Now, since light cannot travel faster than on these diagonals, because that's the speed of light, putting in a light barrier that right after this point where the honest prover would answer cannot influence whatever this verifier and this verifier get here, because the light that is blocked by this light barrier cannot travel faster. So putting the light barrier here will still not change the attack probability. However, now with all these dotted and black lines, we have actually partitioned space into two important regions. Let's call them the left region and the right region. And these two regions, they start with whatever state is here in the universe and is here in the universe, but they don't communicate. So what we have here now is a situation where the adversary has some state here, no communication is possible between the two states, but he can have constructed these two states in some very complex way. But from this point on, there's no communication between this region and this region, and at this point in time, we choose randomly a basis and say, please try to measure what psi was, given what you have here and given what you have here without communication. And there's an earlier theorem from the paper before by Thomas Michael, Fehr, Kaniewski-Wehner, which says that measuring a state psi in two separated space regions, when you get a random B, when you're already separated, this is not possible. And after this transformation, we can use this fact and show in this transformed game, the adversary cannot win, therefore he cannot win in the original game. And that concludes the security proof, or the high-level sketch of it. However, it concludes it only for the 3D case, for the 1D case. I mean, this was very one-dimensional here. And so in the 3D proof, we have a problem. If we try to do the same, we have like the region that can reach this verifier and the region of signals that can reach this verifier. Here they are split by the light barrier because they were non-overlapping. In the 3D case, it turns out if we do the same, we have partially overlapping regions, so it doesn't work anymore. And the solution to this is that we need to program the random oracle not at the same time in every point in space, but at different times at different points in space. And we need to make sure that you don't notice that it changes in different points at different times. So this is for the 2D case, a picture of the surface in space-time when you have to program the random oracle. So it gets complicated. But fortunately, we have to deal with this. We found a new tool called space-time circuits that allows us to handle these things without having all this awful geometry of these things. And it even gives us the same result in curved space-time, so you can do general relativity. So let me quickly say the open problems. The error tolerance for noise should be improved. Also the precision in the 3D case, I can't tell you why there's a problem, but there's room for improvement. And we would have liked to have security in the standard model, or if possible, even without hardness assumptions. Thank you for your attention.